cleanup with respect to other such graphs. So for two graphs like this, each one will be deterministically and immediately cleaned up as soon as it's not being used by the program. But within the graph, I still get to have cycles, which is kind of nice, and run real destructors. This picture should be familiar because this is graph. An example is a graph object which you might own by a reference count, or maybe put on a stack, or whatever it is you do. And whenever it's destroyed, it lets go its internal node. Another example is a region. I want region lifetime deallocated once. So run real destructors if I put a non-trivially destructible object in it. That works fine. But now what if we flip this and we go the other way? Let's say we have, instead of this direction, we go the other way. I now have a deferred heap that contains a deferred object that has a shared pointer or something. It has a whole tree of objects, because maybe that object inside the heap is vector or map. That's perfectly fine. It owns stuff itself. Now the whole data structure has a deferred lifetime. It can participate in cycles with other such data structures, not in the gut, but between themselves. And the entire graph of lazy lifetime, but when I do destroy it, the reference counted object gets ordered, nested cleanup at exactly the same statics step. I just run this destructor, and it can do arbitrary work and own arbitrary things. An example here might be a tree object that has lazy lifetime because you want it to be internal no destruction within the tree. So this could be the very same tree we saw here at the beginning of the talk, but I just did a deferred heap.make tree. So I want the whole tree to have deferred lifetime, and that's fine. When I showed this over the last couple of days to Hans Grohe, he mentioned to me, so thank you very much, Hans, that in Android, the huge majority of Java finalizers essentially do exactly this. This is a picture of what happens in Android when Java cleans up C++ objects. And they've currently been doing some work into special purpose that case, and write special purpose code to specialize that case because it's so common. But it would be nice to do that without having to combine two languages when that lifetime is appropriate. You say you want cycles among these kinds of objects. So we talked mostly about leak freedom, but you might have noticed that there were two other problems that we kind of talked to them along the way. One of the other problems with today's standard smart pointers is the unbounded pointer copy cost. So if I assign one shared pointer to another, that's a simple little operation, right? How expensive could that be? Sky the limit. Because if the destination was the last shared pointer keeping a huge tree of objects alive, that's got unbounded cost. Which is why I've learned that in real-time systems, you often don't need pointers, not smart pointers, not the unique pointers or shared pointers. I'll pick out shared pointer because with unique pointer, you know you're going to get a destructor tree run when you collaborate, so people are more careful. A shared pointer, it might happen, depending on whether it's the last one. And so that tends to be the case that people are more concerned about. They can't see it, they don't know what's going to happen. So you might exceed your time execution deadline if you do all that destructor work internally. And again, you can apply the techniques we saw before, which is to put the destructors off inside yourself. You can do that, and that's a perfectly acceptable way to work around that problem today with today's smart pointers. The other problem that we already saw was unbounded destructor depth. And trees can be deep. This is our guaranteed be deep. Well, when we said this is about deferred and unordered destruction, those two words directly apply to these 2 points. By deferring destruction, pointer copy cost is always down. Assigning the deferred pointer is always cheap. In fact, in the previous version of the repo, if you go back to check it, you notice it's actually trivially copied. And for now, I just store an extra pointer, and it's easy to go back to that if you wanted to make it actually trivially copyable. Why? Because the work gets pushed out to the constructor and the destructor to register and deregister itself, and not to collect. But just copying a deferred pointer is bound and cheap. So this is running a destructor. That means you can use it just fine in real-time code. And as far as stack limits, well, the fact that it's unordered means that when we do run the destructors, even in the place that we do run them, we don't run them nested, we run them iteratively. If we store each destructor, we've nulled out any pointer and deferred pointers between those objects, and then destroy them by themselves. And again, they can go an arbitrary reason Is it the ultimate all-bent thing everybody should use? No, it's a demo. Please give feedback. If you do decide to play with it, please let me know how it goes. If you find bugs, please let me know. And it does have more total cost. We are doing more work. We are storing the structures. Now, maybe you're doing that by hand yourself anyway, so maybe that would be a watch. You have to see what your situation is. But we have to set the mark fit, and we have our own allocator to make sure that we have the right mix in order to do tracing. So the guidance I'm giving you is still use scopes first, then use unique pointer, then use shared pointer. But in the order 1% of cases where you need to ensure an object that will be destroyed when it's no longer needed and those don't work, then defer destruction somehow. You can get ideas from this and still write it yourself by hand as you do today, but defer destruction, do and/or do tracing if you need to, for those remaining cases that aren't already handled well by what we have in the standard. So, it's an experiment. Please let me know how you think it goes. But remember, don't forget that the major point of this talk was that the first slide summarizes the guidance we give people today in one person. And that is a simple answer that will work very well for many people. And then the rest of the talk is applying it to increasingly demanding situations and how to do it safely to get close to safe by construction. So, any questions on the talk? We have a few minutes left. Yes, you've been waiting patiently.
Yes, I just wanted to mention on one of your slides, you're saying to use make share. Should you all, if you have for should you also use make unique just in case your instructor won't grow?
Yeah, and on that slide, use make unique for the unique part of it.
I had a question about diversity. So, once the structures of anything that's unreachable whenever you call it life, but it never deallocates the memory until the end. Could you have unbounded memory growth if you kept on adding new nodes to the graph, but you had unreachable nodes?
So, the question is about memory growth. So, the deferred heap's current allocator will simply ask for more pages as it needs them. And then, whenever you call collect, it will collect deferred objects. It does not currently get rid of empty pages. That would be easy to do. It does not currently do that.
So along the same lines, if you make deferred heap only for like a single type, could you use moves to actually compact your heap and release stuff back to the operating system?
Could you actually use moves to compact the heap? Perhaps. It's very nice that we have move operations now, because without them, you wouldn't want to just do that. So compacting does not work for normal C and C++ types. They are allergic to that because every so often they have countries themselves. Extreme implementations typically do that. So they do not expect their addresses to change. And so you need to respect that. However, if they're movable, you could do something like that. That's true.
Have you considered using separate abstractions for internal and external pointers such that when an isolated subgraph of internal pointers becomes unreachable, collect can be run automatically?
I have not considered yet. I don't want to make it more complex than there's a need to. I'm happy to consider just concept pointer, but I have not yet considered it. As far as running collect automatically, there is an option there already to, by default, that you run it explicitly, but there are ways to opt in to run it, say, when you allocate, but before you allocate a new page, pointers are on that page, and you can tell what different pointers are in this live allocation. And so that's how it does it. Yeah. Is that Eric?
Yes. No, I agree. Yeah.
So not a question, but I have a interview question by Mike Abrash to lead the binary tree without using recursion processes. It can be done, and I'm pretty sure it's generally so we don't have to make any exercise. Also,
So with that, you're saying that destroy a binary tree, retain a binary tree without using recursion.
and without using the heap.
Interesting. Find me afterwards. I'm going to ask you how is that different from the first iterative one that I showed, which has a bunch of the things registered. That's probably something else you have in mind. So tell me about it later.
And also, because I have a